For the second example, I have a practical filter. And I think you have seen this in the main lectures, but you didn't solve it. So you are given an RC circuit like this. We have a source, resistor, and then a capacitor. This a resistor, and this the capacitor. And we call the voltage across the resistor VR. And because the input is a function of time, those voltages will be also functions of time. The input is, let's call it xt or vn, vnt. It's a function of time, so those voltages also are functions of time. And this one is vc, function of time. And we're looking at the output at those 2 points. Yt, which is the same as the voltage across this capacitor, which is vc. We have done also a similar example in the homework, in the last homework. But those are very important. So practice a little bit, and also if you had to review the Kirchhoff's laws, it's a good time to do that if you forgot them. So what we are asked to do here is find the differential equation relating xt and yt. So xt is the input here, yt is the output. We need to find the differential equation that represent this system, what the system is doing to the input to transform it to the to be yt. Or so for this first one, we only need to apply the what's called the Kirchhoff's current law. So from Kirchhoff's current law, Kirchhoff's current law says that the summation of currents at any node is the same is zero. So if you have current of some value entering a node, there should be the same current should leave the node. So the node will not absorb any current, any power. So if we have a node with multiple connections, say those are entering, those are leaving, the summation of current of all of these currents should be zero. So no current, like the current will not disappear. Anything entering, it will leave. For this one, we just have just this loop, and we don't have any, like, it's not branching, there's no nodes. So basically the same current, which is again, since the voltage is a function of time, the current will be a function of time. The same current will flow through the resistor and the capacitor. Now, IT is the same through R and C. Now, from Ohm's law, the the current is just or the voltage is just the current times the resistance. The voltage across the resistance is the current times the resistance. Okay. Or we can write it as the current flowing through the resistance or the resistor is just the voltage across it, which is VRT divided by the resistance value in ohm. And similarly, also from Ohm's law, but here for the capacitor, the current through the capacitor is the capacitance value of the capacitor times the derivative of the voltage across it. You should be able to remember these for the capacitor and the inductor. They are almost the opposite of each other. You should remember those. I'm not sure if they will be given in the cheat sheet. Now we have those two equations. VCT is actually VCT is the same as YT, so we can write this as C dyT divided by dt. And this one can be also rewritten because the voltage across the resistor is just the voltage at this point minus the voltage at this point. The voltage at this point is the Vn itself. So Vn T minus the voltage at this point is the voltage across the capacitor, because this is a ground, this has a 0 voltage. And the voltage across the capacitor is actually the voltage at this point compared to this point. So the voltage is this point is Vc. So we have Vnt minus Vct divided by R, which is also can be written if we substitute Vc and Vn is Xt and Vc is Yt. So Xt minus Yt divided by R, right? Now those two equations are the same because both are representing the same current value. So we can equate them. We'll have then, let me call this one 1, and this is 2. One equals 2. Therefore, xt minus xt minus yt divided by r equals c dyt dt. And if we multiply by r and then separate x and y, one of them on the left and the other on the right, if we multiply by r and then we'll have xt minus yt equals rc dyt divided by dt. And then xt will be RC and this is a first order differential equation that if we have the input, we should be able to find the output from this equation by solving this equation. but we are not doing this in this course because it's not a calculus course. You can find it using calculus, but there are easier ways to find the output for a given input. Now we have solved the first part, which is just to find the differential equation relation between input and output. The second part, the second question is find the frequency response. How do we find the frequency response of this system? If we know, sorry, go ahead.
Do we need to find the transfer function?
We do we need to do what?
Find the transfer function.
The transfer, we can do that. But there's, if we notice that this system is linear time invariant, there's an easier way.
Okay.
We don't need to go to the time domain impulse response and then convert it to frequency. If we notice that this is an LTI, and do you remember how to check if a system is LTI or not?
Then like make sure it's stackable and scalable, or
Yes. We basically use an input, we put the input as alpha x1 t plus beta x2 t. And the output of that, of a system, if it's linear, then its output will be alpha y1 t plus beta y2 t, where y1 t is the output when x1 t alone is the input, and y2 is the output when x2 is used as an input. And then if we use this combination, the output should be also the similar combination using the same constants. So if this is satisfied, then we say that the system is LTI, and this system is sorry, we say that the system is linear if this is satisfied, and then there's another procedure to check if the system is time invariant. And I'm sure you have seen similar during the first part of the course. You did a lot of examples to check if the system is linear or time invariant in this. And I'm sure we have seen similar systems defined as a differential equations, and those systems are linear and time invariant. So this system is linear and time invariant. Notice that till here we can do those steps for any system. It doesn't need to be a linear or time invariant system. But from this part and from here on, we will rely, or we will use that, or we will benefit from this fact that the system is LTI. Now, by noticing that this system is LTI, you might be asked to verify it using the techniques that you learned in the first part of the course. Verify the system is LTI, and then move to this part, which is finding the frequency response of a system. But now we know that the system is LTI. It was not given in the, let's say for this question, it was not given. We are given this circuit, and we need to find its frequency response. We don't know if it's linear or not. But once we find the differential equation, we know that this system is linear and time invariant. And this will make finding the frequency response easier. Similar to the first example that we solved, since the system is LTI, now if the input is xt, is exponential j omega t, if this is our input to the system, what will be the output of the system. We said that those periodic signals are eigenfunctions of LTI systems. So when they are used as input, the output will be just some scaling and they pass through. And what was that scaling? The scaling is what we are looking for, is the frequency response of the system, right? But this is true only for LTI systems. After you make sure that the system is LTI, then we can apply this. And we know that if the input is exponential periodic function of this form, the output will be the frequency response of the system multiplied by the same input signal. Now we have a pair of input and output. This is actually YT. We can now use this differential equation. We can plug in xt equals exponential j omega t, and we plug in yt equals this, and we solve for hj omega, and then we easily get uh, the frequency response. Let's do that. Now we have this input-output pair, xt equals exponential j omega t, and yt, the corresponding output for this input is the frequency response of the system, scaling the same signal, scaling exponential j omega t. Then plug in those in differential equation. We get, let me rewrite the differential equation just to remember it. Xt equals RC times the derivative plus YT. Then we have exponential j omega t equals RC times the derivative of YT is this, the derivative of j omega exponential j omega t plus j omega exponential j omega t. This is YT. Okay. What's the value, or how to find this derivative?
It's one of the properties, right? Or-
I mean the product of two functions. Like the derivative of the product is the derivative of the first times the second minus the derivative of the second times the first, or something like that. Notice here that this one, let me write it in blue. This one is not a function of time, right?
Yes.
We are doing the derivative in terms of t. So this is a constant, or
So
better way to say it, not like constant in general, but independent of t, not a function of time. So it's constant when we are considering t as the variable. So we can take it outside the derivative. and this will be RC times the frequency response omega times the derivative of the exponential. Plus h j omega exponential j omega t. Okay. The derivative of this one is just we multiply by j omega. So this will be RC h j omega multiplied by j omega multiplied by exponential j omega t plus h j omega exponential j omega t. Now, and also on the other side here we have e to the j omega t, right? Because xt equals e to the j omega t. Now we can cancel all of these terms together. Therefore, we have 1 equals RC times j omega times h j omega plus h j omega. And if we solve for h j omega, we get, if we just take h j omega common factor and then we divide by whatever we get here, we get h j omega equals 1 divided by RC j omega plus 1. So, or 1 plus j RC omega. And RC are just, those are the resistance value and capacitance value. So you just deal with them as some constant, some given constant. Or those are mainly design parameters. And at the end, you will find that this is, this circuit is actually a low-pass filter. So it should, and it's not ideal. If it's ideal, then its frequency response will look like this, right? It will look like this if it's ideal. And we have some frequency here. We call cutoff frequency. That's called omega c. So any signal that has a frequency higher than omega c, it will be completely absorbed or attenuated. It will not pass through. Anything is within this frequency range, it will pass through without being touched, without being scaled or anything. And this, let's say this is 1 here. If it's ideal, but this one is not ideal. This will be implemented using circuits, and those elements are not ideal. So the impulse response of this system, sorry, the frequency response of this system would look like this. And here is 1. And at some point here, we have that cutoff frequency. This is minus this omega c. And we consider this as the pass band of the filter. And we can say that the signals that are having frequency higher than omega c will be attenuated by too much or by a high factor, and we assume that yes, they didn't pass the filter and they are filtered out. So comparing this to the ideal, in the ideal case we have this. completely cuts at those frequencies, but for this practical filter, it will look like this. And those cutoff frequencies are actually just 1 divided by RC. So you can choose the values of RC, R and C to design this filter, to move this cutoff frequency to the right or to the left. If you want the filter to allow higher frequencies to pass, you can shift it to the right or make RC smaller. The cutoff frequency will move to the right and so on. Now, I think we're out of time, but I'll give you something to think about, and we might do it in the next session. Is A, B, now C. Find the output for this input, which is sine 2 divided by RC T. Do you know how to do this? It's very similar to what we have done in the example number 1. We have the frequency response of the system, and we know that the system is LTI. We know that the system is LTI. Then, similar to what we have done in the previous example, we know that the output will be, if we want to represent it as a Fourier series, will look like this, and assume that the coefficient for this signal is AK, then this will be AK times the impulse response, or the frequency response, sorry, JK omega naught exponential JK omega naught E. You will use this one. So as in the previous example, this one is given. You just need to find this, and it's easy for a sine. You don't need to do any integration. You just use Euler's formula, rewrite this sign as an exponentials, and then simplify it a little bit, and then you will find the coefficients without doing an integration, similar to what we have done here in this part. Yeah, here. Just write the sign as using Euler's formula, simplify it, and then you will find the coefficients directly. Once you find the coefficients, you plug in this summation, and then you need to evaluate the impulse, the frequency response at K omega naught. And the K's basically will be the ones that are for the coefficients that are non-zero, and you'll get YT. And from here, you should expect that the frequency of this signal is two times the cutoff frequency, right? Because here we said that the cutoff frequency of this signal, the cutoff frequency of this system, sorry, or this filter, is 1 divided by RC. And our signal in this question, XT is given with a frequency in here. So 2 times the cutoff. So you should expect the output to be very attenuated signal. The amplitude of the signal at the output should be small, because this filter will try to filter out this signal because it has a high frequency, higher than the cutoff frequency. And the higher you replace this two, if you replace this two with a higher value, then your signal will have higher frequency, and then it will be decayed even more. It will be, yeah, the output, I mean, will be much smaller when you increase the frequency of this signal, because it will be filtered out. And that's actually the job of this circuit, is to filter higher frequency, and higher as compared to this cutoff frequency. So this cutoff frequency can move to the right and left higher than this cutoff frequency, and that's why we call it low pass filter. I think let's stop here. Thank you for joining, and if you have any questions, please let me know. I'll also stop the recording.